All right. So, thanks a lot for the invitation to speak here. It's a pleasure. I think I've never given a seminar at UKZN, and I had the opportunity to visit before, but I never took it up because other things got in the way. So hopefully at some point I'll be able to visit in person. But I have good friends over there with Kabi and Yinje. So yeah, it'd be great to visit at some point. But we're doing this remotely. So you're gonna hear from me about this topic, cosmology from projective large-scale structure. And there's, I guess, two key terms here in the title that I'd like to start by kind of discussing a little bit. The first one is large-scale structure. The second one is projected. Okay, so let's see what I mean by that. Okay, so large-scale structure, when I say large-scale structure, I'm mostly talking about the idea in cosmology of trying to extract information about the cosmological parameters, about the contents of the universe, the dynamics of the universe from the fluctuations in the distribution of matter in the universe, right? So the quantity that we care the most about is this quantity called the matter over density. And we want to look at its evolution as a function of time, and then its distribution, the distribution of inhomogeneities in this matter density on different scales. Okay, so that's essentially large-scale structure is the set of techniques we have to go about exploring this matter over density. And now, when I say projected large-scale structure, what I mean is the set of techniques to study large-scale structure that deal exclusively with two-dimensional data sets. So by projected, what I mean is that we're not going to be looking at for example, three-dimensional distribution of galaxies, but instead we're going to be looking at two-dimensional projections of those three-dimensional distributions. Okay, and so to give you an example of what that means. The best example probably of an experiment or a type of experiment that delves into projected large-scale structure is photometric redshift surveys. So as you probably know, in a spectroscopic survey, you measure the spectra of specific galaxies that you've previously identified. And then in that case, you have a redshift for those galaxies, which means you have a good estimate for the radial distance to those galaxies, right? And so you can do some kind of three-dimensional analysis of their distribution. In a photometric redshift survey, instead, what you have is a measurement of the fluxes of those galaxies in relatively broadband filters or bands in frequency. And then that means that you're going to have a very poor estimate of the actual spectrum of the galaxy, which means you're going to have a very poor estimate of the redshift of that galaxy. Okay, so the best you can do is maybe have a really rough estimate of what the redshift is, and then put together all galaxies into chunks of redshift, which we call redshift bins, but not really tell the individual radial distribution of those galaxies, right? Okay. The good thing about photometric surveys is that you're able to do this for all the galaxies that you can actually observe with your survey. So you get much higher number densities. And usually these surveys, because you target more or you focus more on getting good images of these galaxies, means that you have good image quality. So you can do gravitational lensing studies, which I'll talk a little bit about later. Okay. So the key players in this field have been so far these three experiments that you have down here, particularly in the field of cosmology: the kilodegree survey kits, the hypersuprime cam HSC, and the dark energy survey, the DES, which you've probably heard about. I should say I'm really happy to take questions anytime. So if you want to interrupt me, go for it. You don't have to raise your hand because I won't be able to see it. So just ask a question if you have any question. Okay. All right, so in the future, all of these surveys are going to be superseded by new experiments. In particular, one that I'm quite excited about is this, the Rubin Observatory, the Legacy Survey of Space and Time, or LSST, which, you have some specifications there. Essentially, it's going to cover a much larger part of the sky to a much deeper magnitude. And it's going to do that very quickly. So we'll be able to cover the sky essentially about 100 times, once every 3 days, more or less. So if you're trying to do cosmology with LSST, you can do that in 5 different ways. So there's 5 different cosmological probes: supernovae, clusters, strong lensing, and then the 2 that I've highlighted in red, which are the ones that I'm going to be focusing on: weak lensing and galaxy clustering. So these are the 2 projected probes of the large-scale structure that LSST will be able to use. Okay, so let's think a little bit about what these probes are and how they allow us to study the large-scale structure. Okay. So first, galaxy clustering is the idea of trying to use as a proxy for what the matter over densities are, looking at the distribution of galaxies, the distribution in the overdensity of galaxies themselves, right? So the idea is if there's more galaxies in a given part of the sky, that probably means that in that region of the universe there's more matter. Okay. So of course that relationship between the overdensity of galaxies and the overdensity of matter is in general actually quite complicated. If you try to characterize it completely on all scales, it's a function that is extremely complicated. It's non-linear, it's non-local, and it's stochastic. There's good reasons to believe, both experimental and theoretical, that on sufficiently large scales, there should be a very simple relation, right? You can imagine taking a Taylor expansion of this very complicated relation, and then on large scales, you'll get something that basically corresponds to a linear relationship between delta G, the overdensity of galaxies, and delta M, the overdensity of matter, with an unknown parameter, B, which is what we call the galaxy bias. And you need to determine that from your own data, okay? This is an approximation that will only hold on large scales. The other interesting property that will become relevant later for galaxy clustering is that it's a local tracer of the large-scale structure, meaning that if you're looking at the distribution of galaxies at a given set of redshifts, you're then sensitive to the matter fluctuations at those redshifts, okay? All right, so the other probe I mentioned was weak gravitational lensing or weak lensing, and I'm sure many of you have an idea of how this works. So essentially you have a galaxy or some source of photons in the background. The trajectories of these photons are going to be perturbed by the intervening large-scale structure due to gravitational lensing, gravitational attraction. So that's going to modify the trajectories of these photons, which means that by the time you observe them, you will see the image of this galaxy as having been distorted in different ways. So first of all, you'll see the galaxy slightly displaced from the true angular position that you would have seen it at if there was no weak lensing. And secondly, and perhaps more importantly, you're going to see a distorted image of the galaxy, right? So it's going to be the shape of the galaxy is going to be slightly changed by the gravitational lensing effect. And in particular, you can show that if you have a lens, basically a massive structure along the line of sight, the background images of your galaxies should tend to align tangentially around that source. Okay, so you'll get a slight ellipticity for your galaxies that will tend to align itself with the tangential direction around the source. Okay, so this is a very subtle effect. This is extremely exaggerated in this picture. In practice, you need many galaxies, and you need to average the shapes of all of these galaxies in order to actually be able to detect this effect with any significance. And this is where photometric surveys come in very handy, because they actually have lots of galaxies, right? So you can observe lots of galaxies and actually build the statistics that you need in order to detect this signal. So the useful thing about weak lensing is that, unlike galaxy clustering, is an unbiased tracer of the large-scale structure of the matter fluctuations, because all gravitational lensing is caused by all the matter in the universe, not particularly galaxies or anything, right? So it actually probes the full matter distribution. So anything that causes gravity will cause weak lensing. But unlike galaxy clustering, is not local. It's a line-of-sight integrated effect, which means that if you're looking at the weak lensing effect of galaxies at a given redshift, you're not actually sensitive to the large-scale structure at that redshift, but at the intervening redshifts, right, along the line of sight between that source and you. Okay. So if we put some math into it, and I promise I will not try to do too much math in this talk, but basically, if we think of the cosmic shear, which is the true kind of observable that we think about when we're thinking about weak lensing, so that's the distortion to the shape of the galaxy, the ellipticity of the corresponding galaxy. This is gamma here. How that relates to the intervening matter fluctuations along the line of sight is an integral along the line of sight, along the radial direction of a kernel that we call the weak lensing kernel, or the weak lensing efficiency function, times the matter overdensities. And what's important is what is the shape of that lensing kernel. You have here the equation that involves the actual redshift distribution of your galaxies, but the point is more easily made in this plot. So yes, if in this plot, basically what I'm showing is what happens if you had galaxies at redshift 4, for example. So you had all your galaxies at redshift 4, and you're reconstructing the shapes of these galaxies and looking at the cosmic shear or weak lensing effect. The lensing kernel is something that peaks at intermediate redshifts between that redshift 4, and redshift 0, where you're observing them, right? So you're sensitive to all the structure along the line of sight, not particularly at the source. And in particular, you will always be sensitive to some extent to the structure at low redshifts, right? Because you will always get a contribution that doesn't reach zero until you get exactly to redshift zero. So you're always going to have some sensitivity to structure at late times, and particularly late times in this case. Okay. All right. There's one last probe that I think is important to note, which is CMB lensing. So this is the lensing, the gravitational lensing of the photons coming from the CMB. So the principle is exactly the same as with cosmic shear. You have photons coming from the cosmic microwave background that were emitted at redshift 1000. And the trajectories of those photons will be distorted by the large-scale structure, which means that they will leave an additional imprint on the angular fluctuations in the temperature of the CMB, right? And it turns out, and you can ask Kathy, for example, to explain how that works to you. It turns out that if you look at the correlation between those the fluctuations in the CMB, you are able to reconstruct the gravitational lensing potential, or effectively the projected distribution of matter fluctuations that caused that gravitational lensing. So it allows you to basically build another map of the intervening matter fluctuations. Okay. So I haven't got into a lot of detail. The main thing to bear in mind when you think about CMB lensing is just think of it as another weak lensing probe. It's just that it's a weak lensing source that is at really high redshifts, right? So a redshift of about 1000, and so the corresponding kernel looks like this black line here. Okay. So as you can see, it's something that will correlate, or that will give you correlations with the matter fluctuations at almost any redshifts, any cosmic times throughout the history of the universe, because it extends almost all the way to the Big Bang. Not really to the moment of recombination, but pretty much. Okay. Okay. So those are the probes that I'm going to be talking about. The question is, how do we then extract cosmology from these probes? Okay. Okay. So I'm not sure how many of you are cosmologists, how many of you would label yourselves as maybe galaxy evolution experts or other experts in other fields of astrophysics, but there's this slide that I always present nowadays, because so basically once I was complaining to a colleague of mine who's a galaxy evolution person that when cosmologists like me go to a galaxy evolution seminar, someone shows a plot of property A and property B and the scatter plot from some survey and the line that goes to the scatter plot, and everyone in the room except for the cosmologists are very excited, and the cosmologists have no idea what's going on, basically, because we don't really know about galaxies very much, right? So I was being slightly rude, and she said to me, okay, but it's exactly the same when we go to a cosmology seminar and anyone shows us a power spectrum, then all the astrophysicists in the room are kind of bored and not very excited about it. So I made it my mission to basically have a slide that very quickly explains what a power spectrum is, and this is that slide. Okay. Right. So a power spectrum, what we do in large scale structure is essentially we try to extract information from fields, right? Things that are defined, quantities defined as a function of position in space or position on the sphere. And a very good way of extracting information from that is by looking at this quantity called the power spectrum, which is a very simple thing. So essentially what you do, you take your field, you put it in Fourier space. So you do a Fourier transform, you decompose it into its different sinusoidal components. And then you take those Fourier amplitudes and you square them. And that's what the power spectrum is. Okay. So the power spectrum, when you see a plot of the power spectrum, it's just telling you the amplitude squared of fluctuations as a function of scale, so the wavelength of those fluctuations, okay? And because it's in Fourier space, on the right-hand side, you have small scales, actually. So large values of k correspond to small scales, and on the left-hand side, you have large scales, which is small values of k, okay? And so we're going to be talking not about three-dimensional fields, but projected fields, as I said. So these are things that are not defined in 3D, but on the sphere. And so the only thing you need to do in that case is, instead of doing a Fourier transform, you do a spherical harmonic transform. But the interpretation, and then you square that, the interpretation is exactly the same thing as in the three-dimensional case. The result is something that we call the angular power spectrum, CL. But you can literally think of it exactly the same way. So on the y-axis of the CL plot, you will have the amplitude square of a given field as a function of a wavelength. That wavelength is this quantity called the multipole L, and literally you can think of it as the inverse angular scale in radians that you should be thinking of. Okay, so if you have L of 100, for example, that corresponds more or less to about 2 degrees in the sky. Okay. So with that out of the way, let me show you what power spectra look like. So this is what for example all the cross correlations, cross power spectra. So now instead of just one field and squaring that field, what we have is 2 different fields and we multiply them in Fourier space. So these are all the cross correlations between bins of galaxy clustering and bins of cosmic shear or weak lensing in a particular survey, in the DES survey, in particular the year 1 release of DES. And what you have here is all the corresponding angular power spectra between them. And so you can see that some of them you can detect really, really well. Some of them you can't really detect very well. And we'll look a little bit at why that is. So the combination of galaxy clustering and weak lensing is what you've probably seen mentioned as the so-called 3 times 2 point analysis. Okay, so what does that mean? Because I'm going to be talking about that for a while. That means you have 2 different types of probes. You have cosmic shear or weak lensing and galaxy clustering. And so if you have 2 quantities and you're looking at 2-point correlations or 2-point power spectra, there's 3 combinations that you can look at: either shear with itself, galaxies with themselves, or then the cross correlation between shear and galaxies. Okay, so you have 3 2-point correlation functions. That's why we call it the 3 times 2 point analysis. Okay. And so I want to give my own kind of description or my own understanding of how we extract cosmological information from the 3 times 2 point analysis. And I think that in the picture I have in my head is that it's best to think of it as 2 different things. So we separate the shear autocorrelation on one side, and what I'll tell you this is going to tell us about is the overall clumpiness of the universe. So how clumpy, how big the fluctuations are. On the other side, if we put together shear galaxy and the galaxy-galaxy correlations, that will tell us about the growth of that structure. So how that evolves as a function of time, right? That amplitude of fluctuation. So let me try to convince you that this is how it works. All right, so I think this is the only other piece of math that I'm going to be showing. It's good to try to understand what the relationship is between the 3-dimensional quantities that we would like to study, like this 3-dimensional power spectra of in particular, the power spectrum of the matter fluctuations. That will be the P of K. And the angular power spectrum, which is what we actually observe. And the relation between the 2 of them is basically an integral along the line of sight of the radial kernels associated with the 2 tracers that we're looking at. So it's an integral of that times the power spectrum evaluated at a particular physical scale, which is the angular multiple L divided by the comoving distance to that redshift. Okay. All right. So essentially, what you're doing is you're integrating this 3D power spectrum over distance. Okay. And distance and scale are related in this way. Okay, so with that in mind, let's think of the shear components of the 3 times 2 point analysis. Okay, so in this case, you only have weak lensing, and we said 2 things about weak lensing. It's unbiased, so we can use its amplitude to say something about the amplitude of fluctuations because we don't have any bias that to marginalize over. But also, more importantly, is line of sight integrated. That means that if we had galaxies with a redshift distribution more or less like this, centered around redshift 1, for instance, what we're actually sensitive to is the intervening structure, which means that the weak lensing kernel is something that actually peaks at intermediate redshifts and then goes to 0 at redshift 0, but slowly. So first of all, that means that with weak lensing, we're going to be less sensitive to evolution because we're integrating over all of these redshifts at once rather than kind of like going redshift by redshift, right? We're actually putting all of these redshifts together in a single quantity, which is the angular power spectrum. We're going to be less sensitive to evolution, and also we're going to be more sensitive to small scales. And that's easy to understand if you just, this is something that we all know. A given something that is closer to us looks larger, which means that the same angular separation between 2 points corresponds to a very small scale if that object is at low redshifts than it would if it was at high redshifts, right? So this is expressed here in a slightly complicated plot that I'm going to try to explain. So what this plot is showing is the 2 solid lines show you the contribution to an angular power spectrum from cosmic shear of different physical scales, so different parts of the matter power spectrum at different scales. Okay, so you have a physical scale in the y-axis, in the x-axis, sorry. So if we fix L, so this the angular power spectrum at L of 100, and I said that's about 2 degrees in the sky. That's a fairly large scale. What we see is that we're actually recovering, if we look at the green line, we're actually recovering information from fluctuations that are on relatively small physical scales, right? So if you go, if you still go to K of 1, so that's about a separation of about pi megaparsecs actually. So that's what we would call a small scale in physics, in cosmology. You're still getting a significant contribution from that to your angular power spectrum, and that's this tail that you have here on the right hand side is purely coming from the low redshift tail of the weak lensing kernel, just because you're sensitive to all this structure at low redshifts that looks very large in the sky. Okay. And then if you want to go to smaller scales, so the typical scales that we go to in weak lensing is L of about 1,000, so that's about 1/10 of a degree. Then you're definitely extremely sensitive to small scales. So anything at K of 1 or above is very, very small scales for us. And in fact, you get a strong contribution from them. Okay. So you're going to be sensitive to evolution, not very sensitive to evolution, and very sensitive to small scales, and particularly from low redshifts. And the other thing is because you're integrating over all these many physical distances, right? You're putting all of them together into a single angle that span many different actual physical separations. That means that you're going to wash out a lot of the structure that you would see in the matter power spectrum. So I forgot to say the dashed lines here. This is the shape of the matter power spectrum that we would like to recover. You have this interesting structure here with these wiggles called the baryon acoustic oscillations, and this rise here on small scales due to the contribution from dark matter halos. A lot of that kind of disappears when you plot the corresponding angular power spectrum. And that's because all these scales have been mixed together by this very large radial kernel. So this plot shows the measurements of the actual cosmic shear angular power spectrum for the third data release of the DES galaxy survey. And what you can see is that it's a very, very boring function, right? It looks like pretty much just a power law more than anything else. So the most you're going to be able to extract from a measurement like this is essentially the amplitude of this power law power spectrum, and maybe a little bit about the shape. So that means that if you use only cosmic shear, you're gonna be able to mostly use the amplitude of this power spectrum, and you're gonna have a very strong degeneracy between the two parameters that control that amplitude. And so that is these two parameters, cosmological parameters that we know as omega m and sigma 8. Omega m basically tells you the fractional amount of non-relativistic matter that we have in the universe. And sigma 8 tells you how large the fluctuations are nowadays at redshift 0. Okay, so you're going to have a combination of them that gives you the right amplitude at the redshift of your galaxies, basically, or the intermediate redshifts. So you have a strong degeneracy between these two parameters, and that's going to show up later. Now let's turn to the second part of this 3x2 analysis, so this shear galaxy and galaxy bits. So in this case, you always have at least one leg, one tracer, which is a galaxy clustering survey, okay, or sample of galaxies, right? And the main thing we said about galaxy clustering is that first it was biased, but more importantly, it's local, meaning that if you have galaxies at more or less well-defined redshifts, right? Maybe they won't be spectroscopic redshifts, but at least you can box them into a relatively small range of redshifts. That means, first of all, that you're going to be sensitive to scale dependence, right? Because now a given angular separation, angular scale, will correspond to a very specific range of physical scales K, right? So it's the same plot as before, but now you can see that if you're looking at a given angular scale, you're actually looking at a very specific range of physical scales, and you can actually isolate what we would call large scales, so anything that is of the order of 0.1 and below, from small scales, which are things from 0.1 and above, basically, especially closer to K of 1. Okay, so you're going to be more sensitive to scale dependence. For example, you're going to be able to recover these wiggles in the power spectrum. And you're going to be also more sensitive to evolution, just because you can use galaxy clustering to slice up your matter fluctuations into different redshifts. Okay, and so the way I like to think about it is the following: imagine that you've looked at the power spectrum between a set of galaxies at high redshifts that gives you weak lensing. So that's this gamma here, and then between that and the positions of galaxies, so the clustering of galaxies at different redshifts, that's the G. So if you look at that cross correlation, that will be proportional to sigma 8 squared, because that everything is proportional to sigma 8 squared, because that's the amplitude of fluctuations, times the bias of your galaxies, right? If you look at the autocorrelation, it will be also proportional to sigma 8 squared and to the bias of your galaxies now squared, because you have two legs of G. So that means that if you've done this at different redshifts, you'll be able to measure both the bias and sigma 8, so the amplitude of fluctuations at those redshifts, and you can reconstruct the growth of fluctuations at all of those redshifts, okay? That's what we call tomography. It's another way of calling this kind of combination of a background tracer cross-correlated with galaxies, essentially. So as I was saying, that means that this combination of galaxy shear and galaxy-galaxy, which is what we call the 2 times 2 point part of the 3 times 2 point, gives you information about the growth of structure, the growth of that amplitude of fluctuations that you can pin down with the shear part of the 3 times 2 point analysis. Okay. All right. So from this kind of analysis, what kind of constraints do we get from on cosmology? So this is a plot that is now slightly outdated. This is from, I think, maybe even 3 years ago. But I think it's a good summary of what more or less the state of the art is. So you can get constraints on this parameter sigma 8 and omega m. You have here constraints from DES, an old version of DES, and KITS, for example. And there's two striking things that you get from this plot. First of all, you can see this very strong degeneracy between sigma 8 and omega m, right? So that's the degeneracy that I was mentioning before. Secondly, you can see that there seems to be some level of disagreement between the region of parameter space that is preferred by this weak lensing and 3 times 2 point data, and the region of parameter space preferred by CMB data. So this gray contour here is from the Planck satellite. Okay. So this is something called the S8 tension that I'm sure maybe you've heard about if you have any cosmologists around you. So it's called the S8 tension because due to this degeneracy, the quantity that we usually like to look at is not either sigma 8 or omega m, but the combination that lies in this kind of perpendicular direction, which is the one that we can actually constrain well with this data. Turns out that that's well approximated by this formula. So that's the S8 parameter. It's basically sigma 8, so it's proportional to the amplitude of fluctuations times this omega m, the square root of omega m. Okay, so when you express it that way, you kind of lose that degeneracy, and you're able to isolate the parameter that you can constrain well, which is S8. And the difference between the value of S8 preferred by CMB data and weak lensing data is what we call the S8 tension. So the amplitude of fluctuations as inferred by the CMB at early times and then extrapolated at late times is larger than what you actually measure when you measure it directly with weak lensing. That's the definition of the S8 tension. Okay. All right, so let's try to understand where this tension might be coming from, and I'd like this plot that we made for a paper from last year, which shows a more up-to-date version of the different constraints that there are on sigma 8, omega m, and S8 from these types of data. Okay, and it's still updated, so there's been new results since then, but it gives you a rough picture of it. Okay, so at the bottom you have the two measurements, or two of the measurements that we have from CMB. So what this tells you, this is from Planck and ACT. What this tells you is that the CMB data sets themselves are in agreement with one another. So there's no tension between them. The next set of points down here are interesting. So these are the measurements of sigma 8 and omega m coming from the amplitude of the CMB lensing autocorrelation, right? So this is like shear, but using CMB lensing, essentially, okay? And so that also seems to give you a value of S8 that is in very good agreement with the value that you get from the CMB, which is nice. And it's not a trivial thing, because CMB lensing is not sensitive to the same range of redshifts and cosmic epochs as the CMB itself, okay? And then you have all this set of measurements, all of which involve either cosmic shear alone, and these are the ones that I've highlighted in green. So these are the shear part of the 3 times 2 point analysis, which all get at different levels of tension. They all get lower values of S8 compared to Planck. And then different other combinations. So here you have the 3 times 2 point analysis of DS and KITS. You have other combinations of galaxies with CMB lensing. And yeah, different combinations of all of the data sets that I've been talking about. And you know, at different levels, they all get some level of tension, which oscillates between 2 sigma and 3 sigma, and 3 and a bit sigma. Okay. So, so what could be going on? Let me talk a little bit, just a couple of slides on this paper, which is from a couple of years ago that we wrote together with one of the fellows here at Oxford called Carlos Garcia. So that's him. And so what he did back then was this is when the tension was becoming kind of very interesting, and what he wanted to do basically is put together all the data that existed, analyze it in a self-consistent manner, and see what you could learn from that in terms of first checking whether all the different probes of the large-scale structure were telling you the same thing about this S8 tension, or whether they were not actually consistent among themselves. And also by putting all of that together, you might be able to actually track down what the evolution in this S8 parameter is as a function of redshift, and then see if you can pinpoint where most of the evidence for this S8 tension is coming from, and whether that means that there's some departures from the standard cosmological model or not. So I'm not going to go through the details. This is a very interesting paper, but I want to focus on other things later on. So I'm not going to go through the details. I'll just say this was a tremendous amount of work, having to reanalyze all this data from a consistent point of view to ensure that the analysis was completely kosher, right? So I think it's a really good paper to read if you want a background of how to analyze something from the catalog level all the way to cosmology. So I think it's a good paper. But this is the only plot that I'm going to talk about. This is the kind of money plot of that paper. And so what this shows is, in blue, you have the evolution of S8 as a function of redshift in the x-axis. So the blue tells you the prediction from Planck and the constraints from Planck on that. Red then gives you the constraints on that evolution of S8 as a function of redshift that Carlos got by putting together all the data that was available back then, which means older DES data than we have nowadays, the main KITS data set that we've been using all these years, and galaxies from a set of other surveys, as well as CMB lensing. Okay. So what you can see is basically the evidence for tension mostly comes from this range of low redshifts. So redshift between 0.2 and 0.5, more or less. And it's at the level of 3.5 sigma, basically, when you put all these data sets together. The interesting thing is, if you separate your data sets into 2 different bits, so SD, this is the south patch, which corresponded to DES, and the north patch, which corresponded to KITS, they all actually are compatible with each other. So they're not really internally in tension in that sense, right? Then at the bottom, what's interesting is what happens if you keep cosmic shear in green. So if you only keep cosmic shear but remove all the galaxy clustering information, or if you do the opposite, you keep only galaxy clustering and CMB lensing, but remove cosmic shear data. And what you see is that the main driver for this tension are the cosmic shear data sets themselves, right? So that tension kind of disappears when you remove cosmic shear. It's not like it goes away completely, and it's not like things are in tension between cosmic shear versus no cosmic shear. It's because the error bars just get a bit larger. So they're not internally in tension, but it does tell you that, at least back then, most of the evidence for this S8 tension was coming exclusively or almost exclusively from cosmic shear. Okay, so with that in mind, we can try to think about what the reasons are for this S8 tension. Okay, so if we buy into this result from Carlos's paper that says that cosmic shear, or in general low redshift stuff, is what's causing this S8 tension, what could be the option? So first of all, it could be just a statistical fluke, because at the end of the day, we're still at the level of 2-3 sigma. So we just need to wait to get more data, wait for that tension to become stronger, and then we will worry about it. But that's not very productive. The other option might be that there's actual slower growth than lambda CDM or the cosmological model tells you at low redshifts, which would be a signature of new physics. That would be very interesting. And there's been papers trying to find complementary evidence from other probes like redshift space distortions and other data. And there's a nice paper by Min Yuan, if you saw it last year, that kind of gives you a comprehensive analysis of that. But we're still at the 3 sigma level, so we would need more evidence anyway. The other option, final thing is, okay, if we buy into the fact that this is coming from low redshifts, at low redshift, things are more nonlinear. And what we also saw is that cosmic shear is particularly sensitive to small scales. And those small scales are going to be even more nonlinear than the large scales, right? So the question is, are we getting the nonlinearities wrong? And is that what's causing this low value of S8? So we have two ways of exploring that question. One of them would be to go to high redshifts on large scales and see, is there actual evidence there or not? So if we do our best at those scales, which seem to be a bit safer, can we find evidence there, or is it really completely isolated to the small scales? And then if that is the case, what you can do is you can see to what extent you can reliably predict what the signal should be on those small scales, right? So cross-check the models that you're using for small scale structure formation. All right, so we've looked into these two options recently in a couple of papers. I'll just mention briefly some results. So the first one, the first option, as I said, is to go to higher redshifts. The question is, how do you go to higher redshifts? What probes do we have that are able to probe this high redshift universe? And one thing you can use is quasars, because you can observe quasars to really high redshifts in principle. And in particular, what we did is we recently looked at a sample of quasars called Quaya. So this is the so-called Gaia and Wise quasar catalog, and it's the brainchild of Kate Story-Fisher, if you've ever met her. So the idea here was that the Gaia satellite, which you may know is the satellite that basically measured really accurately the positions of a lot of stars in the Milky Way to look at the dynamics of the Milky Ways and many other interesting science cases. They didn't just look at stars, right? They also looked at quasars, which are quite useful for them because they are essentially fixed points that they can use to calibrate their astrometry. Okay. So they actually looked at lots of quasars, and they actually took the spectra of those quasars with the Gaia instrument. Sorry, with the Gaia instrument. And those redshifts are not perfect. They're spectroscopic, but some of them, many of them are failed redshifts, basically. So they're kind of nice, but they're not perfect. And in fact, there's actually a lot of impurity in the quasar sample from Gaia. So what Kate did here is she combined the Gaia data with photometry from UNWISE, which is a catalog of sources from the WISE satellite, so an infrared satellite, and then use that to basically clean up the sample, remove as much of the star contamination as possible, and also improve the redshifts of the quasars in the sample. So the result is a sample of about 1.3 million quasars. With pretty good redshifts. They're not perfect, but they're quite decent. You can do tomography quite well. And very importantly, they cover the whole celestial sphere with a really good understanding of the transfer function or the window function, meaning the impact of different systematics in the angular distribution of these sources, and going to really high redshift. So this is the redshift distribution on the left-hand side, which, as you can see, can cover quite well the range of redshifts all the way to redshift 3, and even pushing it a bit more if you want. Okay, so what we did here together with Julia Fabian, who's a CMB scientist, we looked at looking at the autocorrelation of the Quaya sample together and with the cross correlation with CMB lensing. So a kind of 2x 2-point analysis using CMB lensing. We split the sample into these two different redshift bins to get some handle on the growth of structure due to using tomography. And just to give you an idea of what a real power spectrum looks like, this is, for example, the power spectrum, the angular autocorrelation in black of the galaxies in the higher redshift bin, and the cross correlation with CMB lensing from Planck in red from the same redshift bin. And so we're actually able to detect the cross correlation with CMB lensing to better with better accuracy than we can detect the autocorrelation. And the reason for that is that there's a lot of shot noise. Basically, the number of the density of these sources is relatively low. So that affects more this autocorrelation than the cross correlation. So we can actually detect this cross correlation at better significance. But in any case, we have a really good measurement of both, which allow us to then measure the bias of these quasars, the amplitude of fluctuations, and also omega m. And one of the nice things of being able to look at these high redshift objects is that, as you can see, if you look at the blue line, which gives you the best fit model here, the power spectra no longer look completely like power laws. You can actually start seeing some of the scale dependence of the power spectrum itself. And maybe it's easier to see that in this plot. So this plot shows the same power spectra just multiplied by L, so that I can show them as being relatively close to flat, so I can show them all in linear scale. And what I'm showing here is the data together with the best fit model in red, and then what happens if I change omega m and sigma 8 away from this best fit model. And so what you can see is if you change sigma 8, what happens is effectively the whole amplitude changes up and down, which is what you would expect if you change the overall amplitude, right? But omega m does something else, right? So omega m changes the actual tilt, the actual scale dependence of the power spectrum. And because we're able to look at all of these range of scales, we can actually tell those two effects apart. If we were looking at lower redshift objects, we would only be able to look at relatively small scales, because all of those other ones would have filtered out of the sky effectively. On these small scales, you would see that the effect of omega m is very similar to that of sigma 8, right? It just changes the amplitude. And so it's very difficult to break that degeneracy. Whereas now, because we can look at these larger scales where the scale dependence due to omega m is more visible, we can actually break the degeneracy between sigma 8 and omega m. And so doing that, we got this result here. So this shows many different cosmological parameters and the constraints that we get from Quaya in blue. I would suggest we just keep focused on this box here, which shows you the sigma 8 and omega m results. And so what you can see, interestingly, is that Quaya, so just this set of quasars can actually, to some extent, break the degeneracy between sigma 8 and omega m, and actually measure each of them individually with a better accuracy than, for example, the dark energy survey can, right? Just with a million quasars. Arguably, and this is completely true, the dark energy survey does a much better job at measuring S8, so this kind of transverse parameter. But if you're interested in omega m and sigma 8, you can actually do a very good job with the quasars. And the interesting thing is also that this is a measurement of sigma 8 and omega m that is coming from a completely different range of redshifts compared to DES, right? So DES is all very low redshifts compared to Quaya, which is coming from redshift 1, redshift 2, etc. Okay. So that's nice. We can break the degeneracy, but more importantly, we compare with the results coming from Planck, which are up here. We do get a slightly lower value of sigma 8, but not in a form of tension, right? We are within 1 sigma effectively of Planck. So we're in reasonably good agreement with the CMB. So that's interesting because this is coming again from high redshifts. This is something that we looked at in a bit more detail in another paper. This is something that was led by Giulia Piccirilli here, who was a PhD student who graduated recently from Rome. And what she did was slice up the sample into more redshift bins, so we could isolate really the highest redshifts of the sample. So she divided that into 3 redshift bins and reconstructed the growth of the history of growth from all the way from redshift 3 to today. And she was able to do that to much better accuracy than we could have done with previous data sets. And in fact, this is one of the highest, if not, I would argue, the highest redshift measurement of the amplitude of fluctuations that we have nowadays. So just to see you what this looks like compared to the literature, our points are in pink here. And then you can see how all the other measurements basically cluster at redshifts below 1 or 1.5, and we have this very high redshift measurement. There's this other measurement here you can find in this paper from the HSC survey. So this is coming from Lyman break galaxies, a sample of Lyman break galaxies, which are extremely promising as a tracer of the high redshift universe. There are some caveats, however, to how you can cook up this number here, and you have to make assumptions about, for example, the luminosity functions of these galaxies, etc. So, it's a different way of measuring it, and it's something that I think needs to evolve. I would argue this is a much more robust analysis because we're making very few assumptions about almost anything in order to come up with this number. Okay, so So the conclusion here seems to be, if we look at the high redshift universe and we focus on large scales, there doesn't seem to be a strong tension with Planck. By the way, Planck is shown here in dashed, right? So it's not like we can see any real strong tension with it. So then if we buy the argument that this seems to be completely dominated by cosmic shear on small scales, then let's think a little bit about the astrophysical models that we have for those small scales. If we ask ourselves what are the main aspects or the main uncertainties we have when we need to model the clumping of matter, the clustering of matter on small scales, something that seems to terrify everyone is something called baryonic effects. And the baryonic effects is simply the observation that baryons, meaning normal matter, doesn't really cluster the same way on small scales as dark matter. Normal matter is something that has pressure, it has viscosity, and that means that when you go to sufficiently small scales, it will cluster in a different way. And you can see that in hydrodynamical simulations, for example. So on the left-hand side, you have a purely dark matter only simulation, and then the version of that actually contains baryonic matter on the right-hand side. And you can see how the clustering pattern is on small scales is different. On large scales, you can see the same structures, but on small scales, definitely different. Okay, so what does that mean? That means that in particular, these baryonic effects can cause a significant decrement in the amount of clustering that you see on small scales. So what we see here is something called the baryonic suppression factor, which is essentially the ratio of the matter power spectrum, including baryonic effects, to the matter power spectrum if we consider dark matter clustering only. Okay, so 1 means everything clusters the same way. If you go below 1, that means that the amplitude of fluctuations on small scales is lower because of baryonic effects. And so the important thing to note is the predictions that we get from different hydrodynamical simulations, and those are the lines, the black lines that you see here. So that span a wide range of suppression factors that can go all the way to about a suppression of about 30% from 1, right? So that's quite a lot, given that we need to be able to describe this matter power spectrum to kind of the percent level. And then the bands show the current uncertainty that we have on this suppression factor if we just use all the current weak lensing data that we have. So if we use that data and those data and say, okay, we want to figure out what is the level of suppression that we would need in order to explain the S8 tension, this is the current uncertainty. So it's still a fairly large amount of uncertainty if we were trying to solve it that way. Okay. So this is a very uncertain thing that we need to understand better. And so we need to build a physical model for what the gas is doing on this small scale. So I'll try to be brief because I'm running out of time, and maybe you guys need to would like to ask any questions. A very simple model would be the following. Let's say that we take all the gas in the universe and we divide it up into 3 different components. We have bound gas, which is virialized. It's settled in the center of a dark matter halo, and it's quite hot due to virialization. Then you have ejected gas, and this is gas that used to be bound, but that has been ejected away from the virial radius of the halo due to outflows due to AGNs, for example. And in doing that, it's probably also got colder, and it's much lower density. And then the rest of the gas is probably in the form of stars, so basically the galaxies that sit within halos. But this is usually a very small component compared to the diffuse gas, and it's mostly relevant on relatively small scales. It's there, but it's less relevant as a component. All right. So then, if we want to describe the effect of baryonic effects on the matter power spectrum, we need to have a model for the distribution of all this gas. And so for that, what we did in another paper I'll show you some results of recently is we used a model called baryonification that effectively uses physical models for the density of all these components. And then it uses a dark matter only simulation to displace the positions of particles within this simulation in order to reproduce the distribution of gas that you have in your model. And from that, you can then measure the power spectrum in the resulting displaced simulation, and that will give you an accurate description of what the baryonic effects would be for that particular simulation. It's basically a way for you to generate these types of simulations very quickly and be able to get a prediction for what the power spectrum should be for different levels of baryonic parameters. So that has been implemented in a code called BACO, which you may have seen in the literature. There was actually a paper, I think, earlier this week where they generalized this formalism to include other tracers of the large-scale structure. But it's a really useful emulator that essentially allows you to get a prediction for the baryonic suppression factor as a function of a 7-parameter model that describes all these different gas components. And it's really nice the fact that it's able to predict this level of baryonic suppression coming from 74 different hydrodynamical simulations to really high accuracy. All right, so I'll go very briefly through the results of this paper. So in this paper, which was also led by Carlos, he did kind of the same thing as before, or the same spirit, which was put together all of the data that we can. In this case, it was only cosmic shear data, but basically he put together all of the DES, HSC, and KITS data that was publicly available at that point, and tried to, analyze it in exactly the same way from the catalogs, and then try to do a joint analysis of them that really gives you the most stringent constraint you can ever get on S8 coming from cosmic shear. And he was able to go to relatively small scales because we were now able to use BACO, which is the first time that all this amount of data was able to be analyzed with that model. So we could be a lot more certain that we were doing the right thing on small scales. Okay. And because I'm running out of time, what I'm going to do is I'm just going to show you the final result, which I think is best summarized in this plot, and then I'll stop and take some questions. So the result is here, right? So you have the constraints coming from Planck in black on the right. The constraints coming from all of the weak lensing data that we have nowadays in blue on the left-hand side, and that's what you get if you don't account for any baryonic effects. And what you can see is that the value of S8 that you get in that case is significantly lower than what you would get from Planck, and that's essentially the S8 tension. Okay. If you then account for baryonic effects, you're able to justify having much larger values or significantly higher values of S8, and most of that tension essentially goes away, right? So you go from a 3-point-something sigma tension to about 1, I think it was 1.5 sigma tension or something like that, so much lower. However, when you put together all this data, which is the first time that this was done, what you can see is that a tension gets generated on omega m. And this is something that I think deserves more investigation. We did look at all the possible systematics in our data that could have caused this. You can always discover more, but we were scratching our heads about this for a really long time. A lot of this tension goes away as soon as you include other data sets, for example, BAO data. But it's interesting to see that tension on omega m is there. It's also interesting when the new BAO data from DESI came out that they get a value of omega m that is, it's not in complete tension, but it's kind of in tension with Planck. It's lower than Planck by a fair amount, and it kind of sits in between our data and Planck. But it's something that I think it's worth looking at. It's not surprising that this happens if we look at this old plot that I was showing you before. And we focus on the weak lensing data, the cosmic shear data, you can see that all of them measure a low value of omega m. And the point is that when you combine them and how those contours align in a multidimensional parameter space, that kind of tendency gets exacerbated, and you get a kind of 2 to 3 sigma tension on omega m. Okay, so I'm going to finish here. There were a couple more things that I want to talk about, but I think I've run out of time, and they were more technical, so I'll just skip that. And just thank you for inviting me again, and I'll leave you here with my summary. Thank you.
Okay, thank you again, David, for the talk. Very interesting results. So we can move to questions from. Let me see. I have questions from Jinji.
Yep.
Hello, David. Hello, how are you doing?
Hi.
Okay, so somehow I'm connecting my screen, so you don't see my camera. Okay, one moment.
I can see you now, I think. Yeah.
Okay, great. Yes. Nice talk. Really interesting. And so I noticed that finally you only get a DESI BAO, a vertical band for the omega m exception.
Yeah.
Wouldn't DESI also measure sigma 8?
Not so far, because they haven't published anything with redshift space distortion. So just from BAO, you can't really say anything about the amplitude of fluctuations. Basically, so I think it will be interesting to see what happens when they publish the redshift space distortion analysis and the kind of full shape power spectrum analysis, because that then they will be able to say something about S8 and sigma 8.
Yeah. So I have a feeling that maybe the Planck has overestimated the omega m value. So maybe falling slightly below 0.3, so that these baron or future DESI, with clustering quantity would pull the thing a bit towards the lower left. That it will solve the SA tension and H tension simultaneously.
Yes.
Because your CMB sensitive to omega m H to the cube. So
yes,
lower omega m would give you a slightly higher H or such. Yeah.
That's right. So that's also something that we discussed in the paper. You can actually lower all of these tensions if you allow for a slightly lower omega m compounded with a slightly higher value of H, basically. So that would alleviate not only this tension but also the H naught tension that I haven't discussed with
exactly.
Yeah.
Just another note that the H wouldn't be raised as high as Adam Rees, but there was a talk by Wendy Friedman that in the Royal Society discussion recently that the paper is not yet published, but in her slides, she showed the H is about her measurement of TRGB, whatever, is about 9 or so. So that to me seemed to be a tendency to go, under the current situation.
That I think that's going to be very exciting. Indeed. There should be more data now coming from ACT, and it's kind of, I think it'll be interesting to see what comes out in terms of cosmological parameters, because it will be more Planck level constraints, I would imagine, or close to that, but with a different experiment. So it'll be interesting to see what happens.
Absolutely.
Okay. Thanks, Gingy. We have another question by Catherine.
Yep.
Hi, thanks for a great talk. I was just wondering if you had any comments about the kind of recent claims that DESI data prefers a dynamical dark energy as opposed to lambda.
Yeah, it's interesting. I don't know I don't think I know enough to first of all to convince myself. Well, okay, I don't know enough to be super critical, I would say, because I'm not a DESI person and I haven't done the analysis myself. But at the same time, I'm not completely convinced of that for two reasons. First, it's kind of weird that it's only when you open the parameter space sufficiently you start seeing this tension, right? So if you only open one of the parameters, so you prefer just having W not equal to -1 but still a constant, there's no evidence of that. It's only when you make it when you make it dependent on redshift that you see something. So I'd like to understand better whether there's any kind of Bayesian kind of volume effect that happens there or not. Probably not, I would imagine, but it will be kind of interesting to see that. And the other thing is, I still don't understand it fully, because I don't think this was discussed in a lot of detail in the papers, or maybe I missed it. But it seems like there was this one point, one of the BAO measurements for one of the LRG samples it seemed to be the one that kind of drives a lot of the tension. If I just look at the plot myself, right, because it seems to be the one that kind of pulls everything downwards, which is kind of where this dynamical dark energy would push things as well. So it'd be kind of interesting to see, to understand maybe better what part of the data is the one that's pushing towards that, and etc. So I'm not sure. I think it will be interesting to see where things land when more data comes from DESI in terms of redshift space distortions as well. But if it persists, it will be interesting, and I'd like to see what that does for structure formation, and whether it can explain any of the remaining kind of S8 tension as well that still is there. Yeah.
Great, thanks.
Thank you.
Okay, thanks for the question, Catherine. We have another question by Kavi.
Hi, Kavi.
Hi, David. Yeah, thanks. That was a great talk. Yeah.
Thank you.
Just on your last part, do you envisage the future cosmic shear analysis incorporating these emulators to marginalize over?
I think so. I think people are actually quite excited about them, and there's been other analysis done by the DS people, and in combination with kids using emulators for baryonic effects that I think are I think the thing is, out of all the techniques that are out there, they seem to be the ones that achieve the highest level of accuracy when you compare them to almost arbitrarily complicated hydrodynamical simulations. You can never be sure that you've actually tested all the crazy physics that you could get in hydro simulations, but at least these are the ones that tend not to fail in any of them, right? So in that sense, it seems to be like a sufficiently flexible model that allows you to basically marginalize fully over this effect. And the nice thing about it, which I really like, is the fact that it's based on a physical model, right? So it's not just basically looking at the shapes of the baryonic effects in different simulations and just marginalizing over that. It actually is based on physical parameters that you can interpret, but which also means that you should be able to use that model to then predict other observables that we should be able to measure at the same time from other probes like Sunyaev-Zulovich or X-ray data, right? So it's a formalism that then allows you to bring in other data that will tell you whether the baryonic effects that you think you're measuring are actually correct because they're reproduced by other pieces of data, right? So that's kind of interesting, I think.
Cool. Thanks, David. Thanks again for the call.
Yeah. Thanks, Kavi. Yeah.
Okay, we don't have more questions, so I would like to say thanks again to David for the interesting seminar today. Hope to see you, everybody, again in our next seminar, I think next or in 2 weeks. So thanks, everybody. Bye. See you.